So, as we have said in the last class that here we are going to talk about whether surfaces can be represented by parametrization. You are seeing something very strange drawn there. So, we are going to talk about parametrizing surfaces and their associated concepts. When we talk about a surface, we are essentially talking about a two-dimensional object embedded in a three-dimensional space. Two-dimensional object embedded in a three-dimensional space. That is what I mean by a surface. Now, please understand that if you have the graph of a function z equal to fxi, if you write z of fxy and draw the graph of it, get the graph of it, then this graph is a surface. But every surface is not a graph, because every surface need not represent a function. For example, this surface that you see, this kind of folded paper, this is like a folded sheet of paper, like a kind of a lasagna, some covering of some food, right, it is, or a folded sheet of paper like this. You are often seen, when it comes out from a very big, earlier you have seen old photos of computer printers giving out sheets of papers which fold down like this. So, this function, for example, is the set of points x y, this function here is a set of points x y. So, this graph represents this surface contains points x y. So, this has points x y such that x minus, so it satisfies x minus z plus z cube equal to 0. Is this a function? The answer is no, because put the point x0 and equal to 0 and y0 equal to 0. So, take the point x0 and y0 and put them to be 0 0. Corresponding to this, you see z can take the value plus, corresponding to this point z can, if I put z equal to plus 1, this equation is satisfied. If I put z equal to minus 1, this equation is satisfied. So, 0 0 1 and 0 0 minus 1 are both points of this surface, but corresponding to a, if it has to represent a function corresponding to this 0 0 point, there has to be only one z, there cannot be more than one z. So, every surface, though it can have an algebraic representation, need not represent a function. So, this is a very important thing that one has to remember, that every surface need not represent a function, even they have an algebraic representation. That is true about curves too. One of the key points that one needs to understand, that there is a desire in us to actually work with functions, because that is what we understand best. If we need to work with any analytical tool of representation, functions has to play a role. So, in that way, how do I now represent any surface which need not be the graph of any function in terms of some real valued functions? That is exactly what means, exactly what it talks about. So, if there is a domain and there is a surface above it, take a point on the domain and get a function which will take you to some point in the domain. So, get a function which will pick up every point and take it to a particular fixed point in the domain, but not fixed means a single point in the domain. That is not in terms of the x, y, z's involved, but in terms of the some these x, y, z points, they can be represented in terms of other variables, and in terms of that other variable I can represent the surface as a function. Means I can have a function which will give me back, which will return me back for every values of the parameter one coordinate of the surface. So, I will put a say uv in a function phi, output would be some x of uv, y of uv, z of uv. So, this particular point, if I change the uv, the point will change. The same two different uv's will not give me the same point. So, that is what is called parametrization. So, now we will define what is called a parametrized surface. So, our aim is to define the notion of a parametrized surface. So, for this we will go to the next page. A parametrized surface is a vector valued function, right, but from R2 to R3. Face is a vector valued function on a domain D in R2. Phi, which takes points in a domain D, a subset of R2 to R3. The geometric surface S S corresponding to phi is the image of phi, D under phi, corresponding to phi is the image So, basically S is image of D. And phi of uv, where uv is some points on the domain D. So, uv belongs to D. If you take a point uv on the domain D, it will give me a point on the surface, and if you change the uv, it will give me a different point. X coordinate, y coordinate corresponding to uv, z coordinate corresponding to uv. Let us first see, if I have a function z equal to fxy, then this graph is a surface which we know, can we parameterize it in this way? So, first step comes in this particular way. So, what we are trying to do is to try to use the idea of a single valued function to talk about surfaces. So, basically what is the thing that we are trying to talk about here is that, okay, here in R2 you have a domain, right, you have a domain. Maybe I should color it up. you have this domain D, and this a function phi is operating on it to give a surface that, so it is a kind of twisting of D itself. So, it is so now that would give a kind of surface this kind of maybe a very twisted kind of thing. So, this phi that you see takes a point here and drops it here, that is what phi is doing. So, this is what the idea of parametrization is. So, let us first look at a function z equal to f x y, and we see whether we can parametrize the graph. So, f is defined on the domain, defined on a domain D, okay. Then how do I write a parametrization? How do my phi is defined? So, phi of u v is defined as u v and f u v, that is, this is nothing but x y z. So, you define x is equal to u, which is x of u v, and y is equal to v, that is y of u v, and z of u v is equal to f of u v. So, z is equal to f of u v. So, x y z. So, this is the parametrization. So, a graph can be parametrized. So, if a function, if you define a surface as a graph of a function, then it can be very easily parametrized. Our next aim would be to talk about tangent planes on the surfaces. These are very important ideas, because they would play a very important role when we are trying to compute surface integrals, because we have spoken about line integrals, a curve in 3D space, we are integrating along that as if something moves, but if something moves on the surface, how do I integrate? So, once we have defined that phi u v, so this phi u v function can also be written in a vector form as x u v. So, these are very useful in differential geometry. What we are doing is, these are the basics of differential geometry. Z u v j vector. Okay. Now, observe that if I have drawn a surface, so I have a surface here. So, here is a surface, this is a surface. Now, if I fix my u, say at u naught, if I fix my u naught, then C of v phi u naught v represents a curve which moves through all the points on the surface whose points are of the form u naught v. So, CV represents a curve. Now, suppose similarly I can do the opposite thing also. I can fix my u, I fix my v at V naught, and that would be some curve which is passing through all these points. So, both these curves will pass through a point, the point u naught V naught. So, at any point V along this curve CV, what is the tangent? How do I represent the tangent vector? So, any point at any point V, u naught V along this curve CV, how do I represent the tangent vector? The tangent vector is nothing but the partial derivative with respect to V of this parametric function, because ultimately it is nothing but restriction of the parametric function itself in one variable. So, the tangent at the point u to C, the curve CU, is given as phi of the derivative with respect to u, sorry, with derivative with respect to v, sorry, this is C is with respect to v, I make a mistake, v. So, it is phi of v that has to be evaluated at u naught v naught, okay. That has to be evaluated at u naught v naught, because suppose we are just looking at what happens at u naught v naught. So, then basically we are looking at this tangent to C, then we can look at a tangent to this is the curve C, CV, and this is the curve BU. So, I can look at the tangent to BU, then the cross product of these two will determine a vector which will determine the tangent plane itself. So, we will see this will determine phi of v and this will be phi of u. So, phi of v is what? Is del x del v at u naught v naught. So, I am trying to, you can try that, this could be at any v, right. So, suppose I am just trying to find it at u naught v naught, right. So, I am trying to find it at that point. So, I parameterized it in both ways, I am trying to find it at that point, the tangent at that point. So, that is how tangent at a particular point at on the surface is found out, tangent plane. U naught v naught k vector. Similarly, tangent at the point u naught v naught, let me tell v naught. So, tangent at the point v naught is given like this, right. So, tangent at the point u naught, so the tangent at the point u naught so, along the curve C at the point is all curves of the form u naught v at v naught, I am trying to find the tangent. So, that is it. So, tangent at the point u naught to the curve B, to the curve BU. BU is given as phi of v is del x, sorry, phi of u, this was phi of v, del x del u u naught v naught I vector plus del del y del u u naught v naught at evaluated at u naught v naught j vector plus del z del u naught v naught at k vector. Okay. So, this is what it is. Now, consider the curve. Now, consider n hat which is actually del phi del v cross del phi del u. This I call the n hat vector. This is the n hat vector, the normal vector, which is perpendicular to the plane containing phi u and phi v, and that plane is the tangent plane. Okay. So, assume that n is not equal to 0. Then the tangent plane is a collection of all vectors which pass through the point x naught, y naught, z naught. If I write, suppose I write x equal to x of u naught v naught as x naught, y of u naught v naught as y naught, and z of u naught v naught as z naught. Okay? If I write this, then my tangent plane is the plane which is consisting of these two vectors. That is a plane which has the n vector perpendicular at u naught v naught, right. The plane which is where the n vector is perpendicular at x naught, n vector passes through the point x naught, y naught, z naught, and is perpendicular to the plane which contains this vector. So, the tangent plane then has to be such that if you take any point x, on the tangent plane any point x from x naught, y from y and y naught, z from z naught, if you take those three vectors in one vector and take a dot product with, basically now it is like this. So, here is n naught n hat and here is x naught, y naught, z naught. Now, if you take any point x, y, z here, then this vector should be also perpendicular to this vector, to n vector, because it is lying on the plane. That is how the plane would be defined. So, that is how the plane would be defined, and thus the tangent plane is defined as n hat dot the vector x minus x naught, y minus y naught, z minus z naught equal to 0. If the n1 and n2 and n3 are the three components of the normal vector, then n1 into x minus x naught plus n2 into y minus y naught plus n3 into z minus z naught, that gives me the tangent plane. So, let us try this out for how to compute, at least for a function whose surface is given, right, z equal to f x y. Suppose z equal to fxy is given this function. So, the graph is a surface and I know the parametrization. So, here phi uv, the parametrization is uv f uv, where u and v are x and y. So, basically what I have done, I have written phi uv as ui vector, vj vector and fuv k vector. So, now I first take with respect to v or u, whatever you want to do, does not matter, v cross u cross v, here v cross u, whatever. So, here the definition they have given is del u cross del v. You can, it does not matter, you can take it in this way or you can take it in that way, it does not matter, because ultimately it will, if you just change it, there will be a change of sign, n will go in this direction, but the tangent plane should remain the same. We will try to go by the definition and draw it, but it is u cross v, okay, we will go by the definition. I think this is the CU curve. Of course, we have to check, I have done it little hurriedly. We will go by the book and do this definition, u and v. See, what happens is when you actually do an xyz curve, if you have an xyz thing here, then you will know what is happening, you will know in which direction these two are pointing. So, whichever way, you can do it in the other way also, del phi u cross del, you can do it in the other way also, it does not matter. I am just going by the book, so that if you read by the book, read the book, because I have defined it in that way, and if you read the book, you do not feel any problem, because it depends on the actual orientation of the curves. Okay, so let us take here. So, here phi of u is I vector plus 0 1 into I vector, 0 into j vector, and del f del u evaluated at u naught v naught, say k vector, and phi of v is 0 into I vector plus 1 into j vector plus del f del v into u naught v naught k vector. Now, if I go by n naught, n hat becomes phi u cross phi v. See, if it was opposite, they would have they would have changed in the sign, minus sign. It would not have made a huge difference. It would look the same. So, anyway, so that you can check out. So, minus del f. So, if you change it and do the thing, you see what the difference you have. So, del f del u naught v naught I vector minus del f del v, sorry, del f del v evaluated at u naught v naught j vector plus k vector. So, at the x naught z, y naught z naught point, these are actually x naught y naught, u and v are x naught y naught. So, my tangent plane should be given by dot product with minus del f del u naught v naught minus del f del v u naught v naught and 1, and that should give me 0, they should be orthogonal, and that would finally give me an expression like this, z is equal to z0 plus z0 is the function value f of x0 y0, and because u is x and v is y, I will write is del f del x del f del x at x naught y naught, because u naught is x naught, v naught is y naught. This whole thing multiplied with x minus x naught plus del f del y, because v is y. It does not matter if you have changed this u cross v, you can change it and see you will get the same result. U naught, sorry, x naught y naught, because they are the same. I put v as y here, and that into y minus y naught. So, if you look at this, what is this? This is nothing but except the error part. This is the first part of the first order Taylor's expansion for function of two variables. This part is left out, error is left out, and that is exactly the tangent value. That is, the curved surface can be approximated very near the point x naught y naught z naught by a plane. That is the meaning. Of course, I do have some time to give another example which is given in the book, which is a very good example, and that is an example of a cone. A cone in this form. A cone you have seen, it is ice cream cone or a funnel in a oil shop or a funnel in a chemistry lab. So, it is like this. This is a cone with vertex at 0 0 0. So, at 0 0 0 we do not talk about any tangent, right, because there can be many tangent planes. So, at any other point other than 0 0 0 we can talk about tangents, right. So, the surface here is given by z equal to root x square plus y square. So, how do you give? Basically what is happening? Your x square plus y square can be parametrized like a circle, keeping z as a value of the radius, right. So, if I put x is equal to u cos v and y equal to u sin v and z equal to u, then x square plus y square is equal to u square, which is z square. So, I have to now find, suppose I find the tangent plane, find the tangent plane at phi 1 0. What is phi 1 0? Phi 1 0 corresponds to u is 1 and v is 0. The cos 0 is 1, so it corresponds to 1 0 1. So, at this point it is asking you to find a tangent plane. So, how have I represented phi u v here? Phi u v is represented as u cos v I vector plus u sin v j vector plus u k vector. In this case, phi of u, del phi del u. So, phi of u, this vector is now given as cos v I vector sin v j vector plus k vector. Phi of v is given as minus u sin v I vector plus u cos v j vector, differentiating with respect to v, and there is no v, so 0 k vector. Here is 1 into k vector. So, now you take n. See, at 0 0 you cannot have, I can have more than one tangent planes, you can visualize that very simply. I can have more than one planes passing through 0 0 0 without touching the body of the cone. So, this visualization is important. So, n hat is phi u cross phi v. So, if I define it like this turns out to be, if I do the cross product, then this turns out to be minus u cos v I vector minus u sin v j vector plus u k vector, and this vector is 0 when u and v are non-zero, they are non-zero. So, if u is equal to 0, then everything is 0, 0, 0, then there is no tangent plane, then it does not make sense because n hat is 0. So, when n hat is non-zero, right. So, we have to consider tangent planes only in those cases where n hat is non-zero. Tangent planes can be drawn, means at any other point. So, basically we are looking at 1 0 point. So, n hat at 1 0 is what? What is that vector? N hat at 1 0 is, if you put u as 1 and this as 0, it is minus 1, this will be 0 and this will be 1. So, it is n hat becomes minus 1 0 1, and then if I want to find it at the point 1 0 1. So, I will have a dot product minus 1 0 1 dot product with x minus 1 y z minus 1. So, what will be ultimately, it will come out to be minus x minus 1 plus 0 plus z minus 1 is equal to 0. So, this will finally give me the tangent plane is z is equal to x, that is the tangent plane. So, with this calculation, with this description of constructing tangent planes to surfaces and how we can write down a surface in terms of two parameters in terms of two real numbers, we end our talk here. With the 6th week ends, and the 7th week where the whole concentration will go into calculating surface integrals, because they will take us to the main theorems of multivariable calculus and vector analysis. Thank you very much.